University of Hawaii. He's a really famous particular work on global warming, and he's going to discuss this 2021 Nobel Physics Nobel Prize related topic, climate sensitivity and also uncertainty. So I introduced him a little bit. He's Dr. G's highly cited author, published more than 200 publications, and received a number of awards from this elected fellow to the AGE and the American Meteorological Society, and received very bigger award called Swedish Golden Mantle for recognizing his distinguished contribution to the climate science. So I come to.
Thank you, Hanchi. It's really a great pleasure to be here and honor to be here. When I see this campus, I am awed still of that. It's beautiful. I know this picture. This is not actually Hawaii. Hawaii is beautiful by its nature, but this is a different kind of beauty I'm seeing here. But also, I'm very pleased that to have the young audience here. Of course, the old colleagues, older people, we folks have done something, but you guys are really going to have much, much brighter future, but also a hard problems on your shoulder. And we are in a very interesting area in terms of in the field of study of this topic of climate or environmental issues. And as I remember when I entered my college, the college called the Nanjing Institute of Meteorology in China, and that is still the biggest college, or now called Nanjing Institute of Information Technology or Information Technology, Science Technology, so on and so forth. But it has the largest school of people to host school to host the people to study meteorology alone, and they are so much bigger than any campus in the world in terms of the number of size, at least by out of 10. Out of 10. So I graduated from that university, and when I entered college, I'll tell a story first. My father, as my father is really not much without much higher education, but as a parents, they always hope their children will get the biggest thing they know, Nobel Prize, right? He said, is there any chance for you studying meteorology and getting a Nobel Prize? That was 40 years ago. In 1978, I entered the college, 45. And I said, absolutely no way. But I'm wrong, because at that time, climate is not a hot topic yet, and just within my lifetime, and before I even retired, I'm so happy to see that my colleagues, and this colleagues, particularly Suki Manabe, I will show you a picture, that I personally, when I graduated at your age of a college student, I had a chance to meet him when he talked to my advisors on his work at that time, 40 years ago. So now let's get to me to the topic today. I'm going to talk to you about global warming and El Nino. And I'm not talking about their relationships, two different topics. But I want to have a take-home message that is, the global warming is not a solved problem in physics sense yet, and much more in terms of how we're going to face it and to mitigate the problem or to make our life better in the warming world. That is even more open. And I want to say in the front that there will be more Nobel Prize be awarded, I think, in this area in terms of how humanity is facing global warming or solving the global warming problem. Well, the El Nino problem is the problem I've worked on 30 years. So, and I want to say something that how my experience of El Nino may help towards at least solving the unsolved, not fully solved global warming problem in terms of physics, as a physical problem. Okay, so that's the key thing I want to talk about. So let me, sorry, I don't know my computer is doing job. Let me move on. Okay, so let me enlighten you with this figure first, and some of you may seeing similar figures, and this curving, this time series is a global mean surface temperature. And so-called global warming, well, if we look at this time series, you can immediately see by your eye, don't need anything else, you can see, it's just I think from the beginning I entered the college till today, in 45 years in the past, you see about a more than a half-degree warming, or close to, I don't know, a clear trend of warming. This is induced by us, or people before us. Okay, we haven't contributed that much yet, because we are young. And the humanities contributed, no question about it. Now, on top of that is the fluctuations. And these fluctuations, and I draw another time series called El Nino index, or Niño 3.4 index. This is the temperature index over the East Pacific. Later I'll show you where it is. And every up and down, major up and down, is get to the El Nino. And lately you are not seeing record-breaking temperatures of global mean temperatures, is because we are not relatively not having very strong El Ninos. We are in the cool La Nina period, and the temperature is not breaking. But just wait. In a couple of years, maybe this year or maybe next, there will be another El Nino coming, and it will be a record breaking. Probably record breaking, another record breaking temperature will be happening in just a few years. It will happen. It's not going to, like, okay, El Nino coming and the global warming go away. They just add together. Okay, that's the two things. So that's why I was talking about that. So let's talk about the seconds for this thing. So, okay, hold on. For the El Nino I'm dropping myself. This is good. So for the where the El Nino happened, this is a more artistic, cartoon drawing something like the equatorial Pacific. The color red means hot ocean temperature, about 26 degrees above. And then cold tongue, there's a cold tongue. It's a shape, looks small, but you can put the United States and China territory in this area. So it's a very big area, and it's just seems that way. And that's much colder. And then there is this arrows indicating the circulation's upward motion, the convection or clouds and precipitation, downward motion. And if it's in the zonal direction, it's x direction, east-west direction, we call it Walker circulation. If it's in the meridional direction, it's called a Hartley circulation. Hartley is a person 250 years ago considering dreaming about the circulation atmosphere. You can see it when dreaming about it, because the people's Europeans, they take trade winds to explore the world. So from that, he inferred that it must be have Hartley circulation, and that's named after them. And the walk is similar. They dreamed about the circulation from looking without nearly much evidence in the upper air. And those people are really amazing. I will show you a little bit later. And then underneath this ocean, on the equator, what you see, this warm water is really high up in the west part of that. Then the cold ocean underneath tend to be this separation tend to be lift up. This lift up is like you brew a cup of coffee tea, and think about this coffee or tea, but let's think of coffee. You have cream pot and you have dark coffee. And if you blow gently, the cream pot high up, that's similar thing. So the wind blows this way, the warm water high up, then the cold tends to surface. If you blow too hard, you will see black coffee, the creams go away. And similar idea. So that's a setup of the climate system in the tropics. And this system is not unstable, not stable. If you slightly push it, it will oscillate, and that's what will create El Nino. Now, global warming, of course, is global, but the major part of the Earth is in the tropics. Okay, so then global warming is that if we put more CO2 in that, it's like you put on more clothes, it's keep it warm. And the global warming, what's happened is that it add another layer, a little bit of gas in the air, it's going to really make the Earth to sweat and become warmer. And this is for sure from the physical law. Now, so the two things I'm going to talk about is because, first of all, let's mention a little bit more El Nino, and then I will talk about global warming. So the El Nino thing is fluctuating and it's changing. It can have a footprint, has its footprint on the global mean temperature because it is nearly a large area. There is a large area during the El Nino warmth. But that not just by its alone. By this alone warming average over the globe will be much smaller signature in the global warming. It also warms somewhere else, can induce the Indian Ocean warming, Atlantic warming, so it warms, spreads over. Similarly, CO2 is global uniform. But if you take CO2 into pieces and then put in a model to force it every, like the roof patch, patch them together, and then you will find that you can do it in computer models. And we cannot do the nature, we can computer models. You will find that there is a local and a global responses. I want to mention that. So now this El Nino is happening, only can happen here. There's no Pacific, except Pacific equatorial region, there is an Atlantic and there is Indian Ocean. There are similar climate modes that cannot be that big. And why is that? If you're interested, you can read a little paper, two-page paper, I think two pages of my paper in 1996, published in Science. And there's a little theory saying why it only happened in this Pacific. But El Nino is called El Nino, the fishermen find that it tends to be, its strength is the biggest in the Christmas time. And therefore it's called Christ child. This is the name of El Nino in Spanish. Okay. Other things I want to say. So the mathematically called phase mark. It is following the synchronization of the sun. And those things now today we can all physically understand why this is happening. Now, but this El Nino, when the fishermen, I was talking to other people, when the fishermen found the El Nino, I think at that time they named El Nino. People at that time don't use this culture name randomly. With the honor, I think they tend to bring some good to this region. Today, we notice that the El Nino brings lots of disasters to all over the world, and it costs a lot. And it can influence everywhere in terms of weather patterns and environment. Even in the ecosystems or the food productions and so on and so forth. Therefore, it can even, if you think about the money is a very important issue. If you value how much it costs, how impacted it is. One of the papers published by people who work on the IMF, International Monetary Fund, it's showing that many countries, their GDP growth rate and their inflation rate about 10%, even to 15% of that growth rate in inflation. Let's say you have a 4% growth rate, and then maybe 0.5% can be influenced by El Nino if the El Nino happens to this country in bad way or in good way. Depends on different countries. So it is really a phenomenon very, very interesting. I mentioned that because I'm going to now transition my topic back to the global warming issue. The global warming issue, when I was a student, we are not really care much. But even that time, this economist heard about global warming, and then soon he published a paper saying that the global warming, if we want to solve this problem, mitigate the problem, it has a cost, because we put the CO2 without being taxed, we just burn it. But because it's causing the loss, causing changes, the damage to society, it has a cost. So he looking at the global warming issue, the economic aspect of the global warming issue. And it turns out the climate global warming issue gets the attention someday is first from these two interesting Nobel Prizes, one for peace, because I think it is worthy. Still, when it was awarded to scientists, I really feel, well, the scientists, it's not a science prize, so it looks like we scientists together are raising this question of danger, and therefore it's good for humanity, and therefore there is a peace prize. And then there is, put some dollar sign on that, although that the quantification, I think I would have a lunch with your two faculties here. We said this is really not, in terms of order of magnitude, is probably not accurate in his earlier work. He later revised his work. But he pointed out the direction and started the problem. And if you start to work on a problem, people unnoticed you first, well, it's so important, it was a Nobel Prize. But what the really one I to talk, because this is not my specialty, so I don't want to speak too much of it. But this is area I'm familiar, although I work on El Nino most time, but any climate scientist on the physical or dynamic aspect of climate will be always attracted to attention to this fundamental problem today our society is facing. And one of the critical questions is how much our Earth's surface, because we are living on this surface, is going to warm up if we double CO2. And the earliest paper published when I was just this kind of child, I was very young, and this paper already saying that if you double CO2 or you half CO2, we tested, and one is red, one is blue curve, and this is a temperature profile from the surface to 40 kilometers above, using just an energy argument, energy balance argument, using use the physics law. They find that there will be like 2 degree plus minus if you double it or half it, or if you remove some CO2 to cool. If you add more, it will warm, and that's the global warming issue, because CO2 has 3 atoms, and all those odd atoms and molecules can absorb radiation in the air so much more. Fortunately, the air is full of oxygen and nitrogen. They don't do as much, otherwise we're much trouble. And this is fortunate, I think. Why this happened, you have to ask God to let our Earth so livable. But anyway, this is at the surface, the balance of the equation is algebraic. It's very algebraic. You learn it in your in middle school, yeah? Middle school, or maybe before that, algebra. See, first simplest equation of algebra. Let's say you have 4 watts per meter square of CO2 doubling due to the radiative forcing. Then the global temperature will change, and how much is changed has a proportional constant called sensitivity. And so if you know this number, then CO2 doubling or quadrupling will produce this parameter called forcing, and which is very accurate. There's no ambiguity, absolutely no ambiguity. So we will get the number of global warming. However, I want to tell you that this problem determines that is still outstanding. Of course, what gets these 2 gentlemen Nobel Prize is that they first give a crack on it, and they almost get it right. At least the range right. So that's what they tried. the Suzuki Manabe was not just stay here for this one-dimensional problem algebra. He then make this later created a climate virtual machine in the computer as the computer becomes better and better, and this virtual machine is getting better and better. And then they calculate that, and I'll show you later with that. Since then, since his effort, and from 70s, today the computer model keep calculating that. But we cannot narrow down this number more accurately. Between 2 and 5 degrees, if you double 2, then different model give different doubts. Of course, I had to debate with me in the morning whether this is a meaningful. We want to find the equilibrium temperature, because equilibrium temperature may take hundreds of years to get it. However, I can tell you that if we are worried about 50 years later, this number still determines very much controls what's happening in the future. So it's important to remember. Now, this guy got a Nobel Prize. If you haven't read much of his work, here is a brief introduction. He noticed that the Earth's surface on the land have little heat capacity, but the ocean, ocean. I live in Hawaii, don't have worry about so much because we are year-round temperature almost same. Ocean has a larger capacity, so that we don't have much signal cycle. So he realized that the temperature change can be by one ODE. If you learn any calculus or differential equation, this will be the simplest differential equations that you will learn. That temperature tends to restore itself to 0, but if we force it, it will move away. And the weather just make it randomly changing. It looks like random in the climate sense. If we take Dr. Meteorologist, he will be mad saying that the weather are noise. Weather are not noise, influence our daily life. But to the climate, this guy first point out, weather noise can drive some changes at temperature, but not very effective. So if you have external forcing, it is more effective. But the climate variability, the predictability of climate, if we do seasonal predictions and the year-to-year predictions, it's because this ocean has larger capacity, so it's easier to have more memory. This lambda is memory. So that's much of the climate predictions come from this number. So this number has two importance. It determines how the future the climate holds. It also determines how today we can predict beyond the weather. Beyond the weather. The weather is not considered noise, but this noise can make some predictability, kick it around because ocean temperature has predictability. And El Nino is one of the examples, a little more complicated than this equation, which I want to demonstrate very shortly. Now, but one problem in the Nobel Prize citation, I say that this is just for students, okay, we're discussing. I don't want to question any with their citations. Their citation is accurate in one sense, but could be misread by others. So I want to point out that because they say they reliably predicting global warming, they reliably predict it's going to warm. They couldn't reliably predict how much it's going to warm. Nobody has solved the problem. So don't think global warming problem is done deal. You don't use that physics and mathematics anymore. I think Boston College students are very good, smart, still studying mathematics and physics as much as you can, because to help us in the future, we still need our intelligence, not just artificial intelligence. We need our intelligence to solve that problem better in the sooner time scale. Okay, so Nobel Prize is win. It's good thing, but it could be also misled. So I want to make sure this is not the case. And whether there will be no Nobel Prize to solve this problem, physics problem, I do not know. But clearly, there are other problems in this equation. In this equation, and the global warming problem, I want to categorize this problem into 3 parameters. We do not really know the forcing. This is the biggest problem. And we even do not know how to define this number. And also, because if we talk about not hundreds years later, we are talking about 50 years later in your lifetime scale, how global warming we're going to do about it. we need to know the inertia, how much this heat is going to be stored in the ocean, and how fast it is. And these three parameters basically are critical towards really mitigating the climate problems seriously or more efficiently or effectively. So let's move a little further on. So I want to put them all together. So I phrase the climate problem in a linear algebraic first order differential equations. Is climate problem linear? If it's linear, why we have the physicists to solve the problem? Even a first-year college student, if you learn calculus, or if you have AP mathematics, you can solve. Why it's not solved? It's a linear problem. I want to say there is. You can take the GCMs. You can put the CO2 in different distributions in parts, then solve the solution by parts, then add them together. That's one test of linearity. If you put the parts together, solve the problem, and then add the solution together, compare with, put them together, and then find a solution. If the two are the same, the parts add together and put them one lump sum together into the model are the same, that's linear. And the accuracy is more than 90% accurate. You know, if we are 90% accurate in our field, it's not in the quantum physics or the precise physics problem. You need to do 99, sometimes many decimals even important. But for us, 90% accurate is good enough. And our climate warming problem is really far away from 90% accurate. We are really far from that. So that's why I want to mention that. It's really mostly linear. And we did an experiment, we put the CO2 up, then cool it down artificially in the GCM, and to see whether the response is really a relatively linear. Again, people done that. There is some delay, and this delay is due to this C, not due to any nonlinearity, much nonlinearity. Therefore, there is a good evidence saying this problem is linear. And these three parameters, if we can determine, then the whole problem is very easy problem. But that is not the case, of course. So let's move on. I don't want to discuss this solution. The papers, there are papers published. If you wish, you can look at these papers. I'm also these papers demonstrating the linearity of the problem in climate. But of course, they didn't phrase that way. They phrase it for other understanding the physical problem. And another problem is that they are not local. Not local in the sense that if the force is in one place and the other place, you put the different parts, they influence not just locally and not one column problem. And what it means, I want to say, is that this problem is the Earth is not a greenhouse, a little greenhouse in your yard. Earth, we can see as a greenhouse effect. Inside the Earth, we have circulation, atmosphere, ocean. We have complicated three-dimensional circulations, and those circulations create color patterns and so on and so forth, create the sensitivity to global warming. And it is really complicated, involve dynamics, involve the patterns. So we need to solve this problem. This lambda is much more involved than a simple constant. That's what I meant to say. And I want to demonstrate that in my solution to solve the El Niño problem. But this was noticed not now. It was noticed 40-something years ago by this Julian Chinese is really the person, a very, I think the single person who produced so many students and so many influence on the field of weather and the climate during his lifetime. But unfortunately, he passed away then to be young. Otherwise, I would think the global warming problem may be better solved with his presence, a little longer presence. But anyway, what he meant, he wrote a report with all those people, and most of them member of academies, and they wrote a report in 1979. basically saying from Suki Manabe's work and Jim Hansen's work, plus other arguments, they say global warming double CO2, it will create 2 to 5 degree warming range. But then he asked, in this report, a very short report, asked a few questions. And basically that one of the key issues is cloud feedback. It's uncertain. They mentioned aerosol as well. And they mentioned that the heat capacity of the sea. So in this coloring with red, yellow is about the lambda parameter. Blue, deep ocean, the sea parameter. And the green part is the human dimension, the human dimension. It is basically how we're going to, how the future holds with how much level of CO2 or other forces related anthropogenic sources like Hanchi was studying is nearly at that time not uncertain. So I wish to again emphasize that from very beginning, in other words, China has formulated the global warming report more or less in the words, but now I also written in the mathematical formula the 3 parameters given CO2, double CO2 given CO2, how the climate is going to be looks like. So this giving the forcing how the time dependency, the forcing is also dependent, forcing is time dependent, but if you're giving a trajectory of forcing or you determine that F dependence, how the global warming pathway is going to be time dependent. Those two are more physics problem, and the climate model is based on solid physical laws. Yet we have not solved the problem. There is no, I think there is no reason to say we cannot determine this number. Some people say it's probably not. The structure instability was made it sounds like very complicated, and I know that. I was trying to also work on that. But I think it is hopeful we can determine the lambda. It's just not solved. Okay, if we say it's unsolvable, then we discourage it. I'm personally going also to try to get myself feet wet, jump into the problem even at this age of my career. So I think it's solvable. Then better solved than today. The other question, I'm as young as you two in most of the audience, I will jump into it, and I'm so happy that here you have a new institute called Science and Society. And this particular problem, global warming, you cannot go away not considering how people react. Our solution, people take it seriously and ought to be taken seriously and react upon that to change the solution. And therefore, this has a strong human dimension. And more than that, it is really influence our life and the future in every way. So that's a very important problem. I'm so happy to see a new institute right here, right in this building, is studied on this campus. And I even think that it's not only the economic issue, it has another dimension, even the moral issue in it. Because it is really much, I don't want to speak, because I'm not an expert in this area, I don't want to say too much about it. And this is a much harder problem, because there we don't have this solid laws of the physics. And I'm not familiar. I still wish to work on it as we work on this problem. Now, this global warming problem, why is so much an issue for lambda and C. F is also here, you can see. But this is, this I think is similar to 5. Similar to 6 will be the same. And even next one, similar to 7, if you come in, will be the same. This is past 100 years so-called historical simulation. Put every force we know, and we know the observation, and the GCM can simulate. If you look at the GCM, GCM simulated well. But then GCM, this green and the different curves are all the GCM simulations for given CO2 scenarios. You can see the spread is getting bigger and bigger. Therefore, in other words, our model tend to fit model by tuning the parameter fit the past okay. But we are overfitting it, or we are fitting it the wrong way, make it look good. When we predict the future, model shows up its flaw. It's very much uncertain. Now, even worse is that if we human act in different way, that we do not know, which we are definitely not going here, hopefully not being here, but somewhere in between. That somewhere in between is very unsettling as well. And of course, the physics part is important because if we can get better information, make it better informed, we can calculate the cost if we're not acting more seriously and where is the problem, where the cost is, probably people will be more happier to act or act more in intelligent way. And that is talking about life and death and the trillions of trillions dollar question. So now what we are standing for this problem in the physics problem? Well, Chinese reported, just summarize 2 GCMs, what they are doing, and that's the uncertainty between 2 to 5 degrees or 1.5 to 4.5 degrees. And this is much, 20 years later, we have much better GCM than about then. Another 10 years or 20 years, not much change. We are talking about 40 years. We are rented, this is the latest one, the AR5, AR6. Now AR6 has this dash and solid. The dash is so-called emerging constraint. I'm not believing this emerging constraint if we don't have a theory. That's not just my attitude. My advisor called Sir Brian Hoskins, I just mentioned that Isaac Held and Brian Hoskins are considered 2 best dynamists still living on this earth. They have this attitude too. So not me, I learned from them, and I think I share with their attitude that if we don't understand, which means we are not able to really know why this is happening, we are in limbo. This is a problem. And we, as a scientist, we really wish to solve the problem. And show you another evidence, which is a problem, that this is what happens in the past 30 years, the trend pattern. This is all what we can do. This is what happened. Model similar to what happened. Look, this curve fits well. Global average. Now you look at the distribution on the ocean temperature. Ocean temperature is most important because it stays. Land follows ocean. Land is more or less slagged by ocean. More or less, I say, not exact. So if you look at this pattern, look at this pattern, this 2 trend pattern, yeah, there are some agreement, but most critical region where I am claimed to be an expert in the Equatorial Pacific region, they just opposite. They just opposite. This no, and all the El Nino projections in the future, published in many Nature papers, I cause that. I don't agree with this conclusion, but I agree with the approach. We have no better approach. Yet, that's a problem. If the El Nino is wrong, then if we look at how the coastal inundations or planning and build something to mitigate the problem, you are in uncertain. You are getting uncertain information to do a large investment. Let's say we will build some dams for protect Shanghai. Well, it costs $1 trillion if you do so, maybe more than that. But then how tall you build? Yeah, if you build it cheaper, build it too much, it costs. It's really an issue, very important issue beyond engineering, beyond your guess. You need a quantification information. And if you look more, the climate models consistently project that it will be a permanent diminishing of cold down or permanent El Nino-like warming, where what we see in the past 30 years and what we simulated is different. And our simulations keep telling us this. Is this going to really happen, or this is due to natural variability? We are not doing it wrong, but just because of natural variability. Yeah. Or this is we are fundamentally doing something wrong. There's no answer. I can claim that I think I'm very familiar with these problems in thermodynamics, yet we don't have the answer. And if you look at, and I think in the lunchtime I have a conversation with me and Panting also, that the climate models do precipitation bad. Precipitation, we want to get it right, but precipitation on the ground is also the heat source, drives the circulations and the climate patterns patterns, not global mean. The different parts have different distribution, climate, warm, precipitation, and storminess, and so on and so forth. If this different, it will be driving everything different. So therefore, if you do local, regional impact, do downscaling, based on the information by producing these models, you are in good luck situation. Okay, you are not in provide best estimate yet. So that's why we have the Nobel Prize winners haven't solved the problems yet. You have a chance to get a Nobel Prize. Not like I tell my father, there's no chance. And I'm maybe a little too old to shoot for Nobel Prize, but I want to encourage you that it's not just for Nobel Prize. Nobel Prize is indicating the problem. It's not really the prize per se. But this is really encouraging. I think you should take this opportunity. This is your time and your opportunity to solve the problem. And of course, for me as a climate scientist, I really wish that before I retire, before I get too old and my mind become too cloudy to do anything, I wish to work on this problem, this model uncertainty, and this uncertainty projection. If we don't do that, then we are less involved in the community, the humanity, the communities as a whole. And we need to understand that. If we don't understand that, science is meant for understanding. We always ask why, and why it has to be. It's not by chance. That's what we like. So we want to really have reliable projections. Not there yet, and far from it. Then we are talking about a solid or maybe best strategy, or not too much, to overdo it, not underdo it, or not in really that we are better, has a better future and a better way to get there as well. Now, how much time I spent? Okay, I already spent so much time. Let me quickly say, there is a successful story which I spent 30 years to contribute to make it happen. I think I wouldn't say did all of that, but I did step on the shoulders of giants and help to quantify this problem. So the El Nino problem, successful quantification of El Nino instability. Now, why the instability and El Nino instability and global warming are the same thing? It's also determining a constant. Instability means how El Nino is close to the growth rate is, how big the growth rate. If the growth rate is too small or too negative, then it is damaged. So it's not it's strong. If the El Nino the damping rate is small, then it's easy to be excited. So it's very important to determine the El Nino strength. Similarly, this lambda parameter, if it's small, it's super sensitive. If it's large, the global warming cannot double CO2 maybe only produce 1/2 degree. Of course, that's not the case. But definitely, it's already indicated not the case from the data. So now let's go to what the giants they can do. They don't have AI. They don't have a computer. They don't have even observational data much. This guy, when he wrote his first thesis paper in 1922, when he's 25 years old, he imagined how the weather systems looks like in the space, in the sky, all the clouds and how the cyclones looks like in three-dimensional structure. Standing on the surface, just observe with little observations on the surface. No balloons in the air yet, for instruments. And he get it right in that paper. Now, before he passed away, he's a senior professor at UCLA, and he had a little data. He has one island, another island, and another island where they have two temperatures met ocean. There are two ocean temperatures, thermometer in the ocean. One barometer in the island for pressure, 3 times Celsius. Now, then he used his physics, logical reasoning, and imagination, saying, well, he found that, this is the modern data. he found these two islands, the two series I pointed out, have fluctuations. The peak is El Nino, the valley, down is La Nina. So the El Nino case, you have two islands warm. So he knows the El Nino is normally warming by fishermen. So from the east coast to these two islands, there is a large scale warming, he imagined, okay, but he used that imagination. And they say if the warming is happening here, warm, underneath, the surface is warm, air above this warm air is lighter, the pressure will be low, the atmosphere pressure will be low over here. And there is a barometer that says high pressure, and that is adequate. Between low pressure, high pressure, you've got to have winds blow to east, because pressure pushes that way. So you don't have wind observation. He imagined there is a wind, of course, which is true. We have the modern data confirm that. Then he further logic that if normally the trade wind blow this way, now El Nino reverse the trade wind or reduce the trade wind, the trade wind presence maintain the cold down upward, cold water. Yeah. Now if the trade wind diminish, the cold water is not coming, the sun is shining, and that will further warm it because it's already warm. So it's going to further warm it. So start with warm, then make the atmosphere change, then change the atmosphere, change the ocean, change the ocean, make the warm even warmer. It's a snowball process. Much like CO2. If you put the CO2 in the air, warm the ocean, warm the earth, then largely warm the ocean, and it will release more water vapor. Water vapor is a greenhouse gas. You exacerbate the warming, then it gets getting warmer. Then other things changes, clouds changes, and the cloud change if it helps. If the stratocumulus cloud over the California and the Peru coast, huge amount, huge area, diminishes, then it will be even warmer. So cloud releasing can make it even warmer. That's China was raising the equation 40 years ago. And that is the most uncertain part. So all those positive feedbacks make things go bigger. That's Japanese is for that El Nino problem. And now you see why I'm talking about the two. The positive feedbacks are important to determine the amplitude of this El Nino and so on and so forth. But this called Japanese ability, he just verbalized it logically. It takes many years to finish business to quantify it. That's way before I was still a little child. He already mentioned that. And but he wrote it in the paper, said, I do not know why El Nino becomes La Nina and oscillate. El Nino is more complicated than global warming in some sense dynamics. Global warming goes straight, El Nino go up and down. So you need another dimension freedom to determine swinging. So this guy is my colleague in Hawaii. He goes, take the ships through the oceans. But at that time, there's no satellite early on. So he took many islands, measured sea level. He found during the 1982 El Nino, the sea level rise in type East Basin, rise 1 foot. In the west, going down 1 foot. Yeah. Remember the coffee analogy. If you blow the coffee cup and pile up on one side, you see the black coffee almost on your side. So this kind of thing happens in the El Nino case. When the wind blows this way, the water rise on the east and going down, sea level going down by 1 foot in the west. Now, in terms of thermal expansion or in terms of look at deep in the ocean, what's happened is that sea level rise and up associated with that is this separation of the cold water and warm water, the surface changes. So deep ocean warms much more due to this dynamic process. So El Nino, we see the surface tip of ice, largely due to the bottom warming than surfaces. However, why the El Nino? This is due to that positive feedback that I mentioned, the snowball due to the effects. But why El Nino go away? What he did is that he took this whole box region, averaged this area, to see how this entire tropical sea level going to change. In the El Nino, west is going down, east is going up, average zero. But before El Nino, that's El Nino is a red circle at time. Before El Nino, the entire region is built up. The heat being sucked from the outside equator to equator underneath the ocean. And afterwards, the heat being displaced to the off the equator, and that you can see. The surface is warm, but a few months later, surface diminished. Why diminished? Because underneath, heat will be taken away, got discharged. And this has a phase delay relationship, and this is making El Nino to oscillate. And Bianchi's is only finding one problem, and that is a snowballing problem. But then there is a another.
Also, just like the general behavioral indicators, sentiment strengths and weaknesses, just time, bad, seated, something like that.
Okay. So now, of course, this problem was argued, but at 80s, no model can simulate. Even we have these machinery models based on the Newton's law, first law of thermodynamics, mass conservation, ideal gas law, for all equation state for atmosphere and for ocean, and even for the microphysics or for clouds or for the chemistry, other conservation, land surface, everything into the model, try to make it Earth system model. You can simulate El Nino today, everybody can simulate. But in the 80s, no model simulated El Nino. And if you put this model into grids and cover the Earth and cover all the oceans, easily go to a million ODEs or even a billion ODEs. So we're going to higher resolution with more grids and more equations to do. So this machine now today can simulate weather and climate very well. As Ming will, I think he will show you evidence that climate models and weather models are simulated very well today. But in the 90s or 80s, they do not simulate El Nino. And the first model simulated El Nino is not based on TCM. It's like Manabi used the one-dimensional model to the global warming simulation, then to 3D TCM. This is a simpler model, slightly simpler, much simpler model, built called intermediate model. Use the physical principles, but use observation to simplify that. You only make it like 1,000 ODE. Only look at the equatorial Pacific, atmosphere, ocean together, couple together, and then he simulated El Nino realistically. And this, I think he and the students were the Chinese associated. And Chinese was trying to work on that then before he came back on that he died. So then his student, a postdoctoral student, finished that. Really first crack on the El Nino problem and that. So, but I came in much later. I came in much later because I got my PhD in the early 80s, then came to US, and then I got a faculty position. And I work on this problem, and I was thinking about the oscillation. If we have oscillation, you need 2 degree freedom. 2 or second order ODE or 1 first ODE should describe it. So I tried to understand 4 problems theoretically, solve the solutions for more, like the model Marquin was doing, analyze it. But then eventually I reduced further to the 2 degree freedom. So the El Nino index I show you is like SRT in this box early on in observation. So this SRT is important indication of El Nino's temperature. But another thing, Wood he realized that ocean, so-called sea level heat content is important. And he found the east-west tilt is balanced by winds. So, but the average is, this 1 degree average is important for El Nino phase transition. So we can see that because this need 1 degree freedom, we don't need 2 because two together, these 2 east and west difference is related to. Mathematically, you can prove that it can be related. There's only another degree freedom you can determine the H mean. You can use the west also determine H mean in the zonal average sense. So that will be the moon pool heat content and the ocean temperature. These 2 degree freedom will be important for El Nino. And then you use the principle to derive the equation. I cannot tell you how we derive it, but you can derive it mathematically, not fitted from data. Derive mathematically, and then it's this equation will determine the R the capital R, not the lambda early R. This is because El Niño-Southern processes are different from global warming. And this tornado can become positive. And there's another damping will control the whole oscillate not go up or nonlinearity not go up. But there's a phase transition due to discharge. And this model, like a swing, it's like a swing has a position or angle swing and the speed of swing movement. These two variables will write down a similar equation like that. But I will not discuss further. I also will not discuss this detail of how to get it. However, because it's derived, you can write a formula how all the feedback reactions imagined, plus he not imagined, later we discovered. All the process really contributed to air, make our new grow from radiation, from the evaporation, from convection, from the everything you can imagine, turbulence and so on and so forth. And you can formulate it and add those processes together in mathematical terms. How do you depend on east-west temperature gradient in the cold temperature? How it depends on the per degree warming, how much winds it produce, or per diameter square wind stress, how much sea level can be tilt. All those can be determined by the physical laws into parameters. Then you lump together, you can really formulate a mathematical formula for the growth rate. Now you can go to the data, calculate it, go to your GCM to calculate. Then look at how the El Niño behavior in the model or in the nature depend on this parameter. And this works. I tell you this works. I'm not going to demonstrate because I'm running out of time. But also that this model can clearly explain the relation between the heat count and the temperature where it was immediately followed up by people after I published that and used observation. And also I show this diagram because the satellite can see the sea level and the heat content, and you can see the recharge to the equator and then displace of the equator very clearly. So this is very well being verified by the observation. And you can utilize this little equation, little model to generate El Niño behaviors as observed very realistically if you use some data to calibrate the growth rate, right, and calculate the frequency, right, then which you can, and then you can get all the behavior like phase locking, skewness, amplitude, and so forth as observed, and not worse than the GCM. So during the recent conference at Melbourne just a few weeks ago, people said, "Did you use your model to predict El Niño?" I said, "Why I should use it?" But he said, "If they are writing a review paper further educating this paradigm for understanding El Niño. So we needed to see whether this had a predictor really for today's El Niño or so on and so forth. So I asked my student to do that. So, and he did more than that, but I want to show, not show results, show a statement, okay, because I think I prepared that statement, because that results he's still preparing to publish it. And this is a little surprising, because what he said that the reach 2 degree freedom oscillator is not far compared with observation. GCMs with millions or billions degree freedom. Their scale is the middle of those potential GCMs. Some better, some good. Worse. Worse than 2, because they didn't get the oscillator, the nature right. Now if we consider additional those exciting El Niños, other basins, variability, other modes and variabilities together with 8 degree freedom will be the average GCM, linear model. And as good as AI, which take all the GCM information, thousands of years integration, learn it, then try to predict El Niño. In other words, better understanding can really is helpful to demonstrate what is the potential predictor and why GCMs are not getting there yet. And we can see the GCMs is not similar to El Niño's dynamics, right? Not similar to El Niño's interaction with the other modes, other variability in time and light. And that is detrimental for their predictability, ability to predict the nature today in the state-of-art models. Spend billions of dollars and billions of much of effort. So we are that, and with that, I want to further. This is just a speculation. Okay, so not evidence. I didn't have any doubts for that. I want to go back to this question: can we or how we should may add more effort to address this question of global security? And that I finished in 5 minutes. So how may we determine all this capacity so that we do physics part of the global warming problem better than today? If we can do that as a community of climate scientists, we are doing a good service to the whole global warming problem, which has another dimension, which is much harder.
Okay.
Now, one way is build the best model. We have tried 4 decades. Each generation is much better. Okay, it's better. At least much better. Maybe overstatement. And the people are trying to use AI technology for parameterizing better the process GCM cannot describe. It's scale too small, or it's too complex, turbulence, or cumulative activity, and so forth. Is very familiar. It is very familiar with that. But I think he will agree with me that it will take a long time. We do not know, because 4 decades didn't improve. You don't expect next year suddenly solve the problem. It's not like that. Okay, so we should have taken a different approach, but not much is done. Because I spent 30 years on working on the problem, similar parameter for El Nino. So now I'm saying that we had a successful approach quantifying an important and complex phenomenon as El Nino used relatively simple thing. So shouldn't we also try to use similar approach to do so? At least we should try better. It is a much harder problem because it is more involved in radiation, convection, and so on and so forth, a moisture process. And this is known to be hard problem. And it's not easy. But there are things we can consider how we did El Nino right, and how we can do this problem, and I'm studying work on that. I want to declare this because I don't want to solve the problem that here's solution. It's not. But I'm willing to invest my next 10 years to dedicate to this problem. Hopefully we can solve some of it or make good progress. To that, I want to call attention to young scientists or students. Think about that because it may be possible, and I see a possibility. And you need to take all that we learned in the field, so that's why it's hard, because you need to read so much. And then it may be possible, but you said, well, that's not unsettling. I think I have bet myself on that. So, my time now. So, I could be wrong, and we may have different opinions on that. But I think, as I can perceive, this is a very important approach for good reasons. I didn't say. Because we, as scientists, we want to have a solid theory, dynamic theory behind the problem, not just thermodynamic. Then, the thermodynamics is going to work. For sure. Dynamically, we needed to know how much is warming, where it's warming, and where the matters, where the disasters, causes are located, and how we should face it better. And that's all dynamics, by the way. It's not some thermodynamics anymore. At least logical dynamics. And this will, I think, help us to do better for the future past. For that, I want to end, and I want to say that the problem I didn't talk about is this will be in the equation. It's F, but it's so much more to develop further down. I do not know how, so I don't speculate. I just said it's a hard problem, and it is a problem going to have probably more than Nobel Prizes going to win in this area. And that said, I summarize what I said in brief statements, which I don't repeat. Thank you for your attention.
Well, the good news is you have a chance to get Nobel Prize. Any question?
can get started.
Yeah.
Well, save the best for the last. So, I'll ask a few, I guess, if I may.
Yeah.
Maybe I'll start with a more straightforward one. You compare the observed surface SST trend 1979 towards 2000 or so. You show the sort of a hiatus pattern, Niño-like pattern. Then you show the free running couple model prediction. This La Niña-like pattern. Then you are putting those side by side.
No, I think this one is observation, one is the historical simulation. Historical simulation.
Right. Yeah. But it's free running, right? It's couple model free running simulation.
With historical forcing.
Right, with historical forcing.
Yeah.
So, I'm not exactly sure what you're trying to convey. You're saying climate models are not reliable, or?
I say the climate models is not predicting pattern right. They predict the global mean temperature, not predicting the pattern right. This is a worrisome because if I may to tell you, if you predict here is cool, there will be more stratus clouds associated. If you predict this is warm, the clouds disappear, the warm is going to go flying higher. And this this is still small minuscule because this is what happened in past 30 years. In the future, as I showed next slide, slides later, we are going to be much warmer. And if this is going to be, if this is staying, hopefully not, hopefully yes, actually, not is going to be a problem, but it's probably it's going not to stay. It's surely going to go to the future warm. And this is indicating at least this is observation. This is not, and this is a climate model. The historical simulation with all the forces included, just without initial condition. So now could be the initial conditions are problem, or it is our force response problem. I would think the force response is a problem in our solution, not just a different.
But I think there is a consensus. I won't say that a consensus, but there is this emerging opinion that the hiatus of what they're seeing here for the observation, that's the most because of the natural variability.
I think that's not settled. That's if you read the recent paper in GRL, and I think Patisti is the last author. His student was the first author. Bunch of authors, they did analysis and saying, I know my former postdoc at Tokyo University also saying, this is mostly largely natural variability, and something probably also saying that. But then another group was saying that, I think Marquin also saying there is a reason for. So there are two camps arguing. I am here not favoring either of saying which one is right. I'm saying this is a problem. We are not simulating this 30-year time scale trend. And this 30-year time scale trend is not a hiatus also, because so-called hiatus is, if you look at that, homological hiatus, the hiatus in this period. And if we like, in the past 5-10 years, we are in kind of minuscule hiatus too. The slowing down the warming. But maybe this is much due to the El Nino activity. And this is natural variability for certain. However, this trend and the pattern associated with this trend could be still a variability, could be not, because we are doing something not right somehow, and that is debatable, definitely.
Right.
Yeah.
In this case, we talked about this quite a bit, and I think we'll say that. For example, why the model is predicting a La Niña-like pattern, that's for very good physical reasons. And if the world continues to be like a La Niña pattern, it will be, in Isaac's words, very weird. there is no good argument why this case. And I can think of multiple ways to make that argument. So I think there are two camps, but I still feel that the natural variability is gaining the upper hand.
Okay. So let's settle this with the theoretical
Right.
saying this what has got to happen, and that's what is lacking. That's in favor of my argument. We need to develop theory. We are saying this is happen, but all those arguments are hand wavy. You have to give me the quantification. Like, okay, if we give me the quantification, this much is due to due to this forcing or this initial condition, natural variability, and that will be good. And so far, people of course do experiments, but a solid quantification, theoretical quantification is not.
Right. Anyway, quickly, maybe I'll just ask you the last question.
Yeah.
Just try to sort of bring the two parts of your talk.
Yeah.
Talk about on insult theory, then you talk about the warming.
Yeah.
And obviously, any really good physically grounded theory has to be predicted,
Yes.
right? I wonder if I put those two pieces together. If I take your theory to ODE, whether you can predict what the insult will be like in a warmer world, assuming you have some basic understanding of the large-scale control. Can you do that?
I think that's a very good question. So what I'm saying, showing evidence is this kind of simple model can predict El Nino behavior in short term.
Yeah.
Now, you are asking, can we predict El Nino in long term? That's what I proposed in my listen to NOAA proposal pending. And what we are saying is that we should be able to use these kind of tools to see whether we can understand, first of all, why each model gives me different projections of El Nino. Okay, so if I, in the model domain, I can say, this model predicts more El Nino, this predicts less El Nino, is due to what? And then I can say, why the, by the way, during this period, historical simulation get El Nino change wrong already, okay, that's for certain. So now we want to say, can my theory, use my theory, say, given the fact that this is a background, this, what we observe is consistent with what we theory predicts, and what we simulate is also consistent with my theory says. And then I have a ground to say how we may to use that. And this is a proposal. So we are thinking the way you are thinking. So thank you for pointing out that. I hope you are in the view of my proposal.
So, any other question? No?
Any question will be fine. Either I get you all confused, I'll get you satisfied. Yes, please.
Based off the mapping model for the observed, and so predicting the temperature in the Pacific will Hawaii be cooler than the west coast of the United States in the coming years?
You mean the climate patterns?
Yeah.
Okay. The climate patterns, you know, in the future, of course, everywhere is warmer, that's for sure. But where the relative warming is important. So that part I contest. Model is getting much messier or much uncertain. Yeah, I already said the 2 to 5 degree warming global mean this is about like 1.5 plus minus error bars in terms of global warming range from different models. Now, in terms of where it's warming more, the error bars will be even worse. So, but to specifically saying whether even East Coast and West Coast, which side warm more. At the moment, I think people are, okay, observation at this path saying the West is warming more than the East. But particular coast may be a little bit different. But in the future, really I cannot tell. And really depend on how the cumulus, the cloud deck we simulate we predict the model can nearly do correctly. The cloud covers eastern Pacific near the California coast to the east half of the Pacific Ocean, east third half of the ocean. I do not know. I really cannot tell because I'm questioning the GCM results and I have no clue myself. Now, can we determine that from the theory? That's what I'm trying to do. Not yet. Nobody, I think, can tell you. I cannot, but I also can tell nobody can tell for certain where this happened. So I think that's what it means debating. Yes, please.
So in the equation, we showed first slide, can you just go over the F value again?
Okay. Okay, right. That's a very good question because I really hope you get my point of these little equations to categorize global warming in the simplest terms. I think I claim this is the simplest terms to divide the problem. So, you know, either here or here, this is denoting CO2, but you can in the future probably adding nitrate or whatever into your that component as well. So this F at the moment we say in my argument 4 watts per meter square. And how this calculated is if you double CO2, you can calculate the radiation impact in flux downward to the Earth's surface. And how much is that? And that number is F. That's in terms of units, watts per meter square, and it's about 4 for double CO2. Now, if you consider other gases in the future, let's say, then you will modify this a little bit. Okay. Yeah. So other two you have to use. This is depend on how human in the future, how human will act. These two less depend on human act. It's nothing to do with human act. This is depend on how it depends on today's climate state, more or less today's climate state. What we see today in the past 30 years or 50 years will determine the next 50 years. This number is deterministic. We just didn't find it right.
All right. So at least you should know what is El Niño and La Niña, right?
Yeah.
How this form this El Niño and La Niña. That's an exam question. All right. Thank you for let's.
Thank you. At least you can read some papers, get more information. But if you're confused, I don't blame you because I'm probably talking. I didn't give you too much background. Okay.